In the previous lecture, we learned how to solve first-order linear differential equations. And that's with the method of integrating factors. So in this lecture, I'd like to do some problem solving with linear differential equations. First example is going to be a mixing problem. So this is example 1. So a mixing problem with changing volume. So we actually already discussed a mixing problem in lecture 2. We set up a mixing problem. So this one's going to be a little bit more complicated. And I've printed it out here, so I don't have to write it out. So here's a problem. We have a 100-liter tank, and it's initially half full of pure water. So I'm going to start drawing a picture. So we have a tank. Say it looks like this. And it's half full of water. So we'll draw that in. So it's initially half full. That sounds like an initial condition. It's not necessarily always going to be half full. Okay. So there's our tank, and it's 100 liters. And salt water is going to flow into this tank. And so I'll draw a pipe coming in. And so we have salt water flowing in. It's coming into this tank. And so this water is flowing in at a rate of 3 liters per minute. And it has a salt concentration of 10 grams per liter. So I'll draw that down here too. And we also have a pipe coming out. Okay. So it says the well-stirred solution is going to flow out of the tank at a rate of 2 liters per minute. So that is interesting. That does not match this number here. So it's actually only going to be 2 liters per minute coming out. Well, what does that mean? That means that there's more water coming in than coming out, so the water level is going to be rising. So at some point, this tank will overflow. And what we want to know is, at the moment the tank begins to overflow, what is the salt concentration? Okay. So that's the problem. Let's start by defining our variables. So we'll say S of t is going to represent the amount of salt in the tank in grams. So we're in grams per liter here. Okay. And our goal is going to be to write a differential equation. That'll be our first goal. Let's also just note, what is our initial condition here? So it's initially half full of pure water, which means that S of 0 is going to be 0, right? Not 50, it'll be 0 because S is the amount of salt. And I just want to point out one thing. So we're actually looking for the salt concentration, not the salt amount. But it turns out it's just going to be easier to write a differential equation for the amount of salt. And then we can either change variables, or we can go through and do the problem, and then at the very end we'll turn that amount that we get into a concentration. Okay, so let's write a differential equation. So what's that going to look like? It'll look like dSdt equals, and if you'll remember from the mixing problem that we did before, we had the following setup. So we had, there are two contributions. There are two things that are affecting how S is changing, right? So there's salt water coming in, but there's also salt water going out. So dSdt is going to be the rate in of salt, right? But what should the units of dSdt be? It should be grams of salt per time, right? So per, what's our time unit? Minutes. So grams per minute. T will be in minutes. So we have the rate in minus the rate out. This is a typical setup for these mixing problems. So the rate out of salt in grams per minute. It's always a good idea to keep in mind what our unit should be, because then we'll be able to check to see if what we write down makes any sense. Okay, so what is the rate in? Well, we need grams per minute, right? And we know that there are 10 grams of salt per liter. That's the salt concentration of this incoming water. But there's actually 3 liters going in every minute. So we're going to have 10 grams per liter, already units here, times, there are 3 liters, not 1, right? So there are going to be actually 30 grams of salt per minute coming in. And what we should see here is that the units will cancel, right, giving us grams per minute. So that's a sign that we're on the right track here. We have the right units. This is grams per minute. Okay, so now for the rate out, we're just going to do the same thing. So how many liters per minute do we have going out? We have 2 liters per minute coming out. So I'll write that. And now I need to multiply that by something that's grams per liter, right? The salt concentration of this outgoing water. Okay. Well, that's going to be a little bit tricky, actually. So, first of all, how much salt is in this tank at any time? Well, you don't have to think too hard about that, actually, right? Because that's this function here that we defined. That's what S of t is, right? It's measuring the amount of salt in a tank at any time. So we're actually going to have S grams of salt per how many liters? How many liters of water is the tank going to contain? And so that's sort of the tricky part here. It's not a fixed amount. So in the problem we did before, it was actually a fixed amount. But here the water level is changing. So we actually need to sort of do a little side problem here. Let's say V of t is going to be the volume of water in the tank. Volume of water in the tank. And okay, well we know that initially V of 0 is going to be 50, right? Because it's half full of pure water. But in general, what is V of t going to be? So it's going to be 50, but then every minute we actually gain 1 liter, right? We gain 3 minus 2 is 1 liter. So for every minute, we're going to gain 1 liter. So it'll be 50 plus 1t, or 50 plus t. So yeah, I'll just say that. So that's because every minute we gain 1, well, why is it 1? 3 minus 2 is 1 liter of water. Right. So my V of my volume is actually a function of time. So that's what I'm going to put down here. That's the amount of water in the tank at any time. And so notice that I get a differential equation where I have both S and T appearing on the right side. So that's pretty interesting. Let's write this in a little bit of a nicer form. So 10 times 3 is 30, and we have minus 2 over 50 plus t times S. So that is our differential equation. I guess we should figure out one more thing. At the moment the tank begins to overflow, right, what is that moment? Well, the tank, let's just write this. So the tank will overflow when the volume is equal to 100, right? Because that's the capacity of the tank. So when V of t equals 100, so we just set 50 plus t equal to 100, and so we get t is 50. So this is when the tank will overflow. at 50 minutes. Okay, let's take a look at this differential equation. So what do we have here? This actually, it turns out that this is not a separable differential equation. And if I didn't have that 30 there, it absolutely would be separable. You could divide by the s. And then we get a function just involving t, and then a function involving s on this side times ds dt. But this 30 that's sort of being added to it, it really screws everything up. So this is not separable. But it is a linear differential equation. And just to make that more obvious, I'll just move this term to the other side. So this is linear, right? We have ds dt plus some function of t times s. Doesn't matter how complicated that function of t is, right? That equals some other function of t, which in this case is just a constant. So this is linear. It's a linear differential equation. And so we can solve this with the method of integrating factors. So let's go ahead and try that. Okay. The first step for integrating factors, if you remember, is to put our equation in a standard form. What does standard form mean? It means that there's no function of t right here being multiplied by ds dt. I mean, more precisely, it means that there's the function 1 being multiplied there. But we already have that, actually. So it's linear and is already in standard form. So we can just go right ahead and calculate our integrating factor. And so if you recall how we did that, call that mu of t. We derived a formula last lecture for the integrating factor, which is e to the power of an antiderivative of whatever this function is here, the one that's being multiplied by the s. We called that p of t in the last lecture. So 2 over 50 plus t dt. Need to do this integral. And that's going to be a natural log. So we have e to the power of 2 times natural log of 50 plus t. Notice because t is just appearing by itself without any coefficient, I don't need to multiply by anything out here. There's no chain rule going on. I also don't need to worry about absolute values because t is always going to be positive here. Okay, so if you recall from last lecture, a trick here is you use the property of logarithms to rewrite this as 50 plus t squared inside the logarithm, right? I just want to make that clear. And now we can cancel the e and a natural log. You cannot cancel them here yet. And we get 50 plus t squared. So that's our integrating factor. And if you recall, what we do next is we multiply through by that integrating factor. Okay, we multiply through this equation, one in standard form. So let's go ahead and do that. So we're going to get 50 plus t squared times ds dt plus, this one's going to become 2 times 50 plus t s. That's going to equal 30 times 50 plus t squared. It's a very common mistake to forget to multiply the right side by this integrating factor. Also, we have to multiply the whole equation by it. Okay, and if you recall, what we do next is we try to view this left side here as a product rule, as a derivative of a product. And so what do we have here? We have s and ds dt. So this will be the derivative of a product if this function right here is the derivative of this one right here. It's always good to kind of check just to make sure we did this right? So the derivative of this function should be this function, and indeed it is. So we did this right. So let's actually write this as the derivative of, so it should be this one here, 50 plus t squared, times this one here, s. So it's the idea from last lecture we talked about. On this side, we'll just write this again. Okay. And now we take the antiderivative of both sides. And so on this side, we get 50 plus t squared times s, and that's going to equal, what's the antiderivative here? It'll be 50 plus t cubed, but I need to divide by 3, so I actually have a 10 times 50 plus t cubed. And very important, I also remember to add an arbitrary constant here of integration. Right. Okay, let's solve for s. So what is my function s of t? It's going to be just 10 times 50 plus t, so it's going to look roughly linear in this bit. But now I have a c divided by 50 plus t squared, like this. Okay. So this is my function, s of t. And let's go ahead and solve this, or finish solving this. So we need to figure out what c is. So we're going to use our initial condition, s of 0 is 0. So we get 0 equals, let's see, 50 times 10 is 500, right? T is 0, plus we have c over 50 squared is 2,500. Okay, so what is c going to be? So I guess it'll be negative 500 times 2,500. So c is actually going to be, that'll be a pretty large number. So negative 1, 2, 5, 4 zeros. So negative 1,250,000. That's what our constant is. So let's go to the next page. So we'll write our function s of t. And what is it? It's 10 times 50 plus t plus, I guess this will be minus now. So minus 1,250,000 over 50 plus t squared. Okay, great. So this is our solution. And what do we want to know? We want to know what the concentration is when the tank overfills. And a tank will overfill at t equals 50. So we just have to plug in t equals 50. Plug in t equals 50. And so we want to know what s is. Well, actually, more accurately, we want the concentration, but let's figure out what s is first. So we have 50 plus 50, that's 100, times 10 is 1,000. Now here we have what do we have down here? We have 100 squared, that's 10,000. So if I divide this number by 10,000, I'm essentially just getting rid of those zeros. So I had 1,000 minus 125, that's going to be 875. So what are the units there? This is the amount of salt, right? That's what S is. So this is just grams. Okay. So we're almost done. We want grams per liter. So the concentration is going to equal 875 grams of salt per how many liters? Well, there'll be 100 liters of water when the tank is full. So we get 8.75 grams per liter as our salt concentration. Great. So we see back in our setup here, we have 10 grams per liter coming in. The water's initially, it doesn't have any salt in it, right? But it ends up having a concentration of 8.75. Okay, so that's the first example. I'd like to do another example. So this will be example 2. We'll call this one a example of an invasive species. Invasive species. So I printed this one out also. So let me put that up here. Okay. here's our second problem that we're going to try to solve. So we have an island community. It's been overrun by rats. And so there are about 7,000 rats, more or less. But their numbers are actually going to grow at a rate proportional to their current population size. So this is something we've seen before. And it says actually assume that the proportionality constant is 0.2 when we measure time in weeks. So, I mean, let's already start writing a little bit down. Like even before we read on, we might have to go back and change things, but if R of t is the rat population, okay, so I mean, we know it's initially 7,000, but we want to study what this is over time. And we already have a glimpse at a differential equation here. So dr dt is going to equal, how is the rat population changing? It's changing at a rate proportional to the population size itself, right? And we know the constant proportionality is 0.2. So it's 0.2 times r, right? So that's the current population size at any time. Okay, but it's not going to be that simple, actually. So we're actually going to introduce a predator to try to control the rat population. So we're introducing cats. And at first, the cats are going to eat the rats at a rate of 1,000 per week. So what is that saying, actually? It's saying that the dr dt is actually, there's probably going to be a minus something here that I'm gonna have to write down. This is causing the rat population to decrease. So initially, dr dt is decreasing by 1,000 per week, but actually the rate at which the cats can eat the rats is increasing. So it's increasing by 100 per week because I guess they're becoming more skilled at it. So it's actually not going to decrease by 1,000. It's going to decrease by 1,000 the first week. I should put parentheses here. So it'll be 1,000 the first week. The next week it'll be 1,100. The next week it'll be 1,200. So in general, it will be 1,000 plus 100t, right? Because they're eating 100 more per week. And the rat population is decreasing by that amount, right? That's causing dr dt, causing the rat population to go down. So this is just on its own, right? This is how dr dt works. It's 0.2 times r, but we have this that we're actually adding on because this is with the predator. Okay. Okay. And finally, we have a question. Will this plan be successful? So how will we solve this problem? We'll do what we've been doing. We'll write down a differential equation, which we kind of just did as we were reading through this. We'll solve this differential equation, and then we can use the solution maybe look at the solution, take a limit of the solution, perhaps, right, as t gets larger, to see what's going to happen. Okay. So there's the differential equation. What kind of differential equation is this? Well, again, this one turns out not to be separable, but it is linear. And that's because we can write it like this. So dr dt, this time will be minus 0.2r equals minus 1,000 minus 100t. A lot of minuses here. It's going to be a bit annoying probably when we work through this, but there's our linear differential equation. So this is a linear differential equation again. And notice the dependence on t here, right? That's interesting. So, and that's because they're getting more skilled as time goes on, right? So there's going to be so it depends what time we're looking at. They'll be better if we look at it long into the future. Okay, so let's try to solve this one. try to go through quickly. So it's in standard form already. That's the first thing we should ask, right? Is it in standard form? It is. Let's calculate our integrating factor. So here it's going to be e to the integral of just a constant this time, negative 0.2. So it's going to be e to the negative 0.2 t is our integrating factor. Okay. And then we multiply through by the integrating factor. And then we're going to rewrite, so let's multiply through by the integrating factor, and then I'll try to do both steps at once. So I'm gonna rewrite this left side as a product, as the derivative of a product. What will that product be? You're probably getting used to this a little bit by now. That product is just the integrating factor, right? Times this function here, times the variable r. And then on this side, we also need to multiply by this integrating factor. T e to the negative 0.2 t. Now let's integrate both sides. So we get e to the negative 0.2 t r is, so I'll take out the constants. So we get negative 1,000 times the integral of e to the negative 0.2 t dt. And then we have a minus, so I'm just using the fact that the integrals distribute over sums, and we can pull out constants. And so we have minus 100 times integral of t e to the negative 0.2 t dt. Okay, so we're almost done. We just need to do these two integrals. This is actually going to be a good reminder of a really important integration technique that we're going to see a lot in this class. So this one we don't need anything special. What is this one going to be? Actually, yeah, let's sort of isolate both of these. So this integral here is just going to be, well, e to the negative 0.2 t, but then out here I need to have 1 over negative 0.2 in order to cancel this out from the chain rule. 1 over negative 0.2, that's actually negative 5. So that's going to be the integral there. If you'd like, you can do a substitution. Substitute u equals negative 0.2 t, and du is negative 0.2 dt. But we get this from that integral. And this one is where we're going to have to use integration by parts. Integration by parts is if you have a product of two functions, and those functions aren't necessarily, they don't necessarily look like each other. Right here we have a linear function times an exponential. That's a good sign you're going to need to use integration by parts. So this one's going to be integration by parts. Let's just review that really quick. So integration by parts, we have the following formula. So if we have an integral u dv, we can actually rewrite that as uv minus v du. And if we cleverly choose what u and dv are, then we can actually make it work out so that this integral over here is simpler than the original one. And so that's the point of integration by parts. You're just rewriting the problem in a different way. It's hopefully simpler. And the way to make it simpler is to choose u to be something that becomes simpler when you take its derivative. Okay? Because we have a du there. So we want this integral to be simpler. So I'd like to choose that t to be my function u. And then we don't have any choice. The rest has to be dv. Okay? And hopefully dv is going to be something that we don't really mind integrating. Like maybe it doesn't become more complicated necessarily. That will ensure that this integral will be simpler to solve in most cases. Okay, so what is this this piece going to be here? So I'm just going to write down it's uv, so it's t times, well I need v. What is v? V is actually just this thing right here, right? That is the integral of dv. So it's t times negative 5 e to the negative 0.2t minus v du. Okay, so minus the integral of v du. T, and then what is du? That's just 1, right? Because u we chose to be t. We chose it to be something that became simpler when we take its derivative. So we get this thing right here. And let's write down what this ends up being. So it's going to be, so we have minus a minus, right? So that's just going to become plus. I'll get rid of that little minus there. Okay, and so we have negative 5t e to the negative 0.2t. And we have to integrate this again. I mean, we already did that. We get another negative 5 that comes out, right? So we do end up getting another minus 25 e to the negative 0.2t. So that's this bit here in red. That becomes this. So let's just summarize. So we have e to the negative 0.2t. I'll copy down the whole equation. And then we have a negative 1,000 times negative 5 e to the 0.2t. So that's going to be a 5,000, positive 5,000, right? 5,000 e to the negative 0.2t. And now we have minus 100 times this. So we're going to get pluses for everything. So plus 500 t e to the negative 0.2t plus 2,500 e to the negative 0.2t. And you'll notice we can actually combine these two. Okay, but before we do anything else, I forgot something very easy to forget, right? I almost forgot it. We took an antiderivative here, so we need our constant of integration. So easy to forget here, right? When we're mired down on all these integrals. Okay, so then let's combine these two to give us a 7,500. And then at the same time, I'll divide by this e to the negative 0.2t. So we get r of t equals, okay, these are just going to cancel everywhere, right? Except for this term. So that c is the key, actually. So we have 7,500. Just going to be the constant, right? Because these all go away. We're actually going to get, it's going to appear over here, right? So we're multiplying both sides by e to the positive 0.2t. Now I'll cancel all of these out, except that it will appear over there. So we have 7,500 plus 500t plus c times e to the 0.2t. And that is our function, r of t. So that was a tedious calculation. I hope you're still with me, because it's about to get pretty interesting, I think, actually. This function has really interesting behavior. So let's go back here. So our initial population was 7,000 rats. So let's suppose, actually, we'll do 3 cases. Just to kind of see the behavior of this, these solutions. I should say these solutions, right? Because this is a general solution so far. Okay. So let's suppose r of 0 is 7,000, as it said in the problem. Okay. Well, let's plug it in. So we get 7,000 equals 7,500. This just becomes 0, and we get plus c. Because we're plugging in 0 for t. Okay. So what does that mean? That means c is negative 500. So let's write our function. Minus 500 e to the 0.2t. Okay. What does that look like? Okay, so I'm going to actually draw a graph here. Okay. So we only need the positive quadrant. Right? So this will be time, and this will be the rat population. Okay. Well, we're starting at 7,000. That's R of 0. And so what do we have? We have a linear function right here. And then we have this bit here. What is this going to look like? So e to the 0.2t, that is an increasing exponential, right? But we're subtracting 500 times this increasing exponential. So here's actually what it's going to look like. Also, I should point out, because it's an increasing exponential, this term will dominate. So this term dominates as t goes to infinity. The exponential beats any polynomial. So it's actually going to look like this. Maybe it's going to be going up slightly because of this linear term. Maybe not even, right? But it's going to go down eventually. I think it's actually going to go more straight across and then down. But this is the key, right? It's going to go down, not only to 0, but to negative infinity. And so what will happen to this rat population? It's going to go to 0. So this plan will be successful. So here the plan will be successful. Okay. Okay. So before I end this lecture, I'd just like to consider a couple more cases. There's something interesting going on here. What if we had slightly more rats? So what if R of 0 is 8,000? Okay. Well, what would C be in this case? We have 8,000 equals 7,500 plus C. So C would be 500, positive 500 this time. Okay. So let me write that out. 500t plus 500 e to the 0.2t. What will that look like? So let's say up here somewhere we have 8,000. That's our starting point. And again, yeah, we have a linear function going up, and we're adding on this increasing exponential. It's plus 500 times an increasing exponential. So if we start with 8,000, we're just going to have a completely different result. This population is just going to explode. Right? So this is like case 2. Okay. And I'd like to do one more case. So see if you can think what that case will be. We're looking at this equation. So what if we have 7,500? What will C be in that case? So you might have seen this already, but 7,500 equals 7,500 plus C, right? So C is 0. So that's really interesting, and that actually kills off that exponential term completely. So we just have 7,500 plus 500t. So we have a linear function. So if this is 7,500, we're going to have a linear function like this. So this will be case 3. And the crazy thing about this is if we actually have any less than this, so if we have 7,499, what will happen turns out we'll get something like this. We'll actually just get minus e to the 0.2t. And that will eventually dominate, but it might take a while. So it'll actually it'll go down to 0, the population. But if we have 7,500, it's actually going to go up to infinity linearly. And if we have 7,501, that's going to go up to infinity exponentially. So this is an example of a differential equation where there's a lot of sensitivity on exactly what the initial condition is. You can change the initial condition slightly and just get completely different behavior of your solutions. So this is an example of that. We'll see more examples of that in future lectures. Okay. So actually, I'm not going to do another problem in this lecture, but I do want to give you an opportunity so let's do, I'll call this example 3, but I'd like you to try this example. So this one I'll call a factory leak. And actually, I created this problem to be sort of a combination of the previous two problems. So you can, if you work through this problem, you'll really get good practice with the techniques we talked about in the lecture today. So we're starting with a lake. It has volume 20,000 cubic meters. And we have a stream coming in and a stream coming out. And they're the same rate, right? So I'll start drawing this. I'm not going to do the problem, but that's going to be for you to try. But we have a stream coming in and a stream coming out. Okay. So here's our lake. And start labeling. So 20,000 cubic meters. Just want to emphasize, drawing a picture is a really important problem-solving strategy. Helps you really organize everything and have a mental picture of what's going on. So we have 200 cubic meters per day. That's the rate of the water coming in. And then we have actually the same rate coming out. Okay. But what's happening? So a leaking pipe at a nearby factory is actually going to release a pollutant into the water of the incoming stream, causing it to be contaminated at this concentration, 50 grams per meter cubed. However, that's actually going to change. So kind of like in the second problem, it's getting worse over time. So it's actually going to increase that concentration of the pollutant by 10 each day. Okay. So first it'll be 50, then it'll be 60 the next day, then 70. So you have to write a little function for the concentration of the pollutant. Okay, and you're going to assume that these are all everything's mixed and there's no pollutant initially. Right? That's what that last bit is saying. So a couple things I want you to try. So you're going to want to define a function for the amount of pollutant. And this will probably be in grams because that's what we're given. And so first step is I want you to write a differential equation. So if you're ever in trouble with this, just go back to the first step example we did in this video. And that one was a bit different because the volume was changing. Here the volume is actually not changing. Right? Okay, so write a differential equation. Second step, solve it, right? So you're going to find a formula for P of t. And then the third step, I want you to consider actually what happens with other initial conditions, kind of like we just did up here. We looked at a few initial conditions, and we got very different behavior. So consider various initial conditions. And let's give a little bit of a spoiler. This also sort of help you check to see if you understand what's going on at the end of this. So, it's a spoiler, I guess. But what you're going to get is, you're going to get some function maybe it looks like this. There's actually going to be a linear function, okay, just like this example where we had a linear solution. So there's going to be an initial condition that gives you a linear solution. See if you can find what that one is. And then if we start above that, we're actually going to get solutions that look like this. Okay, so it's actually sort of the opposite of this situation here. Here we had solutions starting nearby this linear solution. We're diverging away from it. So this is sort of an unstable case here. And here we have solutions actually converging to this linear solution. So this is sort of a more stable situation. And we're going to talk more about solutions like this over the next few lectures. But yeah, definitely try this problem, and I'll see you next time.